Where does our galaxy come from? How did that immense collection of stars, planets, gas, and dust that we call the Milky Way, of which we are a part, come into being? Since humanity first looked up at the night sky and observed that mysterious whitish band crossing the firmament, we have felt a mix of wonder and unease. What is the true story of our galactic home? Was the Milky Way always as we see it today? Or is it the result of chaotic processes and colossal transformations? These are questions as old as human curiosity itself. But today, thanks to science, we have fascinating clues to approach the answers. The Milky Way is not simply a collection of scattered stars in space. It is a complex, dynamic system that is constantly evolving. Like an ancient tree whose roots are lost in time, our galaxy has grown, changed, and survived violent encounters, cosmic collisions, and unexpected mergers. Every star, every cloud of gas, even every grain of dust tells a part of that story. But how did all this originate? What forces and events shaped the galaxy that now houses us? To understand the origin of the Milky Way, we need to go back to a time when the universe was radically different. A universe without galaxies, without planets, without life. Just a primordial sea of particles, energy, and darkness. In that scenario, billions of years ago, the first ingredients began to take shape that, after a long process of assembly and transformation, would give rise to structures as complex as galaxies. The birth of the Milky Way is, in fact, the story of how the initial chaos of the cosmos organized itself into increasingly sophisticated forms. But how did those first clouds of gas and dark matter manage to attract and gather enough material to form a galactic monster like the Milky Way? What role did collisions with other galaxies, the formation of the first stars, or the black holes at the center play? These are enigmas that challenge our imagination and that modern astronomy is gradually beginning to unveil. Understanding the origin of the Milky Way not only answers one of the deepest questions about our place in the universe, but also helps us understand how it was possible, in a lost corner of this galaxy, for life to emerge. The Milky Way is much more than a luminous band in the night sky. It is a gigantic spiral galaxy, our cosmic home, where the Sun, the solar system, and billions of other stars reside. But what does it really mean to live in a spiral galaxy? Imagine an immense city with avenues that curve and intersect, filled with neighborhoods and districts as varied as they are fascinating. That's what the Milky Way is like, but on a scale so vast that it's almost unimaginable. Have you ever wondered how many stars make up the Milky Way? Astronomers estimate that there are between 100 billion and 400 billion stars just in our galaxy, along with planets, clouds of gas, dust, and mysterious dark matter. But the Milky Way is not just a collection of celestial bodies. It is a dynamic and constantly evolving structure where stars are born, die, and recycle their materials to form new generations. Its characteristic shape, with spiral arms that extend like whirlpools, makes it one of the most common and spectacular types of galaxies in the universe. Where do we find ourselves within this vastness? The solar system is located in one of the smaller arms, called the Orion Arm, quite far from the central bulge of the galaxy. If the galaxy were a big city, we could say that we live in a quiet suburban area, away from the hustle and bustle of the center. This location has protected us from many violent phenomena that occur near the galactic core, such as supernova explosions and a higher concentration of radiation. But what place does the Milky Way occupy in the universe? Although it seems enormous to us, the Milky Way is just one among billions of galaxies that exist in the observable cosmos. It is part of a group of galaxies known as the Local Group, where it shares its neighborhood with other galaxies like Andromeda and the Magellanic Clouds. Thus, when we ask ourselves what the Milky Way is, we discover that it is both our home and another piece in the vast puzzle of the universe, a colossal structure that invites us to explore and marvel at the scale of the cosmos we inhabit.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, Don't forget to subscribe to the channel and give the video a like. Thank you for being part of this star odyssey.
How complex can the home of billions of stars be? The Milky Way is much more than just a bright disk in the night sky. It is formed by a fascinating structure, almost like a cosmic city with well-defined neighborhoods and a history of evolution written in its components. But how is our galaxy really organized, and what secrets does each of its parts hold? At the center of the Milky Way lies the galactic bulge, a dense spherical region filled with ancient stars. It is like the heart of the galaxy, a compact sphere brimming with energy where stars are much closer together than in other areas. Surrounding this bulge is the galactic disk, which is the most recognizable part and where most of the stars, including our Sun, are found. This disk is relatively flat, and if we could see it from the outside, it would resemble a huge spinning plate, crossed by spiral arms that slowly wrap around the core. The spiral arms are not just simple decorations. They are regions where gas and dust concentrate, favoring the birth of new stars. In these arms, clouds of gas collapse under their own gravity and ignite the spark of star formation. That's why the arms are like fully operational star factories, filled with young, hot stars that illuminate the galaxy with bluish hues. Why do they take on that spiral shape? The answer lies in density waves, a kind of cosmic traffic that compresses the gas and triggers the cycle of starbirth along the arms. Beyond the disk, the Milky Way is enveloped by the halo, a vast spherical region that surrounds the entire galaxy. The halo is much fainter and contains very old stars, as well as globular clusters, compact groupings of hundreds of thousands of stars that orbit the galaxy like swarms of bees around a hive. Additionally, within the halo lies a mysterious invisible component, dark matter, which significantly contributes to the total mass of the galaxy and keeps its structure together through gravity. Thus, the Milky Way is a masterpiece of cosmic architecture, with a central bulge rich in history, a vibrant disk that gives life to new stars, spiral arms that mark the pulse of the galaxy, and an enigmatic halo that wraps it all. Each of these components plays an essential role in the functioning and evolution of our galaxy, and together they form the stage where the story of the Milky Way unfolds, and of course, our own. What other secrets await us in this complex cosmic web? How big is the Milky Way really? Imagine trying to traverse it from one end to the other. Even if you traveled at the speed of light, it would take you about 100,000 years to cross its diameter. That's how immense our galaxy is. But how do you measure something so colossal? Astronomers estimate that the Milky Way has a diameter of between 100,000 and 200,000 light-years, when considering the more diffuse edges of the galactic halo, that outer region formed by stars and dark matter. To put it in perspective, the distance between the Sun and the nearest star, Proxima Centauri, is just over 4 light-years. So the Milky Way is, literally, an ocean of stars. But size is not only measured in length, but also in content. How many stars are there in the Milky Way? It is estimated to contain between 200 billion and 400 billion stars. How can one imagine such a quantity? If each star were a grain of sand, you could fill several entire beaches just with the stars of our galaxy. However, the Milky Way doesn't just house stars, it also includes enormous amounts of gas, interstellar dust, and a mysterious dark matter that makes up most of its mass, even though we cannot see it directly. Is the Milky Way an especially large galaxy in the universe? If we compare it to many other galaxies, the answer is yes. It is larger than most of the dwarf galaxies surrounding it, but it is far from being the largest of all. For example, the Andromeda galaxy, our closest neighbor, is even a bit larger and contains more stars. However, if we look even further, there are giant galaxies like IC 1101 or the Bode galaxy, which can exceed the size of the Milky Way multiple times over. Now, what does it mean to live within a galaxy of this size? Humans barely inhabit a small corner in one of the spiral arms, called the Orion Arm, about 27,000 light-years from the galactic center. Despite the vastness of the Milky Way, everything we know, from the solar system to the farthest gas clouds our telescopes can detect, is contained within this gigantic cosmic structure. Our galaxy is so large that even though light travels quickly, many of the stars we see in the sky may have changed or even disappeared in the time it took for their light to reach us. Thus, the size of the Milky Way is not just a matter of numbers, but a window to understand the astonishing scale of the universe we inhabit. When we think of the Milky Way, we often imagine an ocean of stars, gas, and dust. But there is something much more mysterious that makes up most of its mass: dark matter. How is it possible that something so important to the galaxy is invisible and, so far, undetectable directly? Dark matter neither emits, absorbs, nor reflects light, making it a completely hidden presence to our eyes and traditional telescopes. However, its existence is crucial for understanding the structure and movement of the galaxy. Why are astronomers so sure that dark matter is there if they have never seen it? The answer lies in the behavior of stars and gas within the Milky Way. If only visible matter existed, the stars at the edges of the galaxy would rotate much more slowly than they actually do. But when scientists measure their speeds, they find that they spin so fast that without an additional gravitational force, they would simply fly off into space. It's like trying to spin a stone tied to a rope and suddenly feeling that someone invisible is holding the rope with you. This invisible force is precisely the signature of dark matter. And what role does dark matter play in the formation and evolution of the Milky Way? Imagine the galaxy as a city built on invisible foundations. Dark matter acts as a cosmic scaffolding. Its gravity held together the first clouds of gas, allowing them to accumulate and form stars and planets. Without this mysterious matter, the Milky Way might never have formed as we know it. Moreover, dark matter is not distributed evenly. It is thought to form a gigantic halo that envelops the entire galaxy, extending far beyond the disk where most of the stars reside. The search for dark matter is one of the great challenges of modern astrophysics. What is it made of? Why can't we detect it directly? Many theories have been proposed, from exotic particles yet to be discovered to new laws of physics. The truth is that although it remains a mystery, dark matter is the invisible glue that holds the Milky Way together, and likely the entire universe. Without it, the story of our galaxy would be completely different, and the mystery of its origin continues to fuel the curiosity of scientists and cosmos lovers alike. How did it all begin? The question about the origin of the universe has fascinated humanity for millennia. According to modern cosmology, the answer lies in an unimaginably small and dense moment, about 14 billion years ago. That moment is known as the Big Bang. But what does this term really mean? It wasn't an explosion in the common sense, but rather an incredibly rapid expansion of space and matter, as if the entire universe were a balloon suddenly inflating. In that first cosmic breath, space, time, energy, and matter were born, laying the groundwork for everything that exists today. In the first moments after the Big Bang, the universe was so hot and dense that even atoms could not form. It was made up of a primordial soup of subatomic particles, protons, neutrons, electrons, photons, and a mysterious presence we know as dark matter. Why can't we see dark matter if it plays such an important role? Because it neither emits, absorbs, nor reflects light, but its gravity was essential for the formation of structures in the cosmos. As the universe expanded and cooled, these particles began to combine. Protons and neutrons formed the nuclei of hydrogen and helium, the simplest and most abundant elements in the universe. Hundreds of thousands of years later, the universe had cooled enough for electrons to join those nuclei and form the first atoms. That moment allowed light to travel freely through space, creating what we now detect as the cosmic microwave background radiation, a kind of fossil echo of the universe's birth. Imagine that radiation as the faint and persistent glow that remains after a campfire is extinguished. It is the imprint we can still observe and study to understand how it all began. From that point on, the universe was like a blank canvas, but it already contained the necessary ingredients for the creation of galaxies, stars, and planets. The slight irregularities in the density of matter caused by small quantum fluctuations in the early moments acted as gravitational seeds. Over time, these denser regions attracted even more matter, leading to the formation of the first giant clouds of gas. Thus began a process of clustering and collapse that, millions of years later, would culminate in the formation of the first galaxies, including the one we know as the Milky Way. Isn't it amazing to think that our galactic home arose from tiny fluctuations in the primordial chaos of the universe? How can a cloud of gas transform into something as grand as a galaxy? To understand the origin of the Milky Way, we must go back to a time when the universe was a much simpler and colder place. Only enormous clouds of hydrogen and helium existed, direct remnants of the Big Bang, floating in an almost absolute darkness. These clouds, known as proto-galactic clouds, were gigantic, with masses equivalent to millions of suns. But what triggered these seemingly tranquil clouds to begin collapsing? The answer lies in gravity, that invisible yet relentless force that governs matter in the cosmos. Where there was a small clump of gas, gravity attracted more gas and so on, in a kind of cosmic snowball effect. Slowly, dense regions within these clouds began to attract more and more material, heating up in the process. This heating was not only a consequence, but also a sign that something monumental was about to happen, the birth of a galaxy at the heart of a shrinking and spinning cloud. Was it a fast and violent process, or a slow and patient transformation? The reality is that the collapse of proto-galactic clouds was an event that took hundreds of millions of years. As the gas fell toward the center under the pull of gravity, it began to rotate. This spin, similar to water forming a whirlpool as it goes down the drain, helped flatten the material into a disk. However, not all the gas fell uniformly. Some regions were denser than others, favoring the emergence of areas where matter was compressed even further, paving the way for star formation. And why didn't the collapse stop before forming a complete galaxy? The key lies in the delicate balance between thermal pressure, which tries to expand the cloud, and gravity, which compresses it. When gravity won the battle, parts of the cloud fragmented into multiple high-density regions, giving rise to the first star clusters. These fragments, as they continued to collapse, ignited the first stars, marking the beginning of a new stage in cosmic history. Thus, from the collapse of gigantic gas clouds, the Milky Way was born, a complex and dynamic structure that continues to evolve to this day. When did the first lights appear in the universe, and what role did they play in the origin of the Milky Way? To answer this question, we must travel back to a distant past, to an era known as the Dark Age of the cosmos. After the Big Bang, for hundreds of millions of years, the universe was dominated by a dense sea of primordial gas, composed almost exclusively of hydrogen and helium. There were no stars, no galaxies, no planets. But in the silence of that vast darkness, something extraordinary was brewing. The birth of the first stars, known as Population 3 stars. These Population 3 stars were very different from those we know today. Why? Because they were formed solely from the simplest elements, with no traces of metals or heavy elements. Unlike our Sun, these stars could reach immense masses, tens or even hundreds of times greater. Can you imagine a star so colossal that it lives only a few million years before exploding violently? That is exactly what happened. Their lives were brief, but their impact was monumental. With each explosion, they released enormous amounts of energy and, for the first time, created more complex elements, such as carbon, oxygen, and iron. Why are these first stars so important for the Milky Way? Because they acted as the seedbeds of galactic chemistry. Their explosions scattered the essential ingredients for the formation of new generations of stars and, eventually, planets. Without these pioneering stars, matter would be doomed to remain in its primordial state. In a way, we can imagine population 3 stars as the original chefs of the universe, cooking the fundamental elements that would later allow the emergence of solar systems, and much later, life itself. But how do we know of their existence if none have survived to this day? The evidence lies in the chemical traces we observe in the oldest stars of our galaxy. Astronomers search for stars that are extremely poor in metals, tracing their composition to understand the legacy of these ancestral giants. Additionally, computer simulations and studies of the cosmic microwave background support the idea that these first stars not only illuminated the darkness, but also influenced the structure and early evolution of the Milky Way. Thus, although we will never see a population 3 star with our own eyes, their story is written in every atom that makes up our galaxy. When we think of the birth of a galaxy like the Milky Way, we might imagine a peaceful and solitary process. However, in reality, its origin was marked by a series of violent and chaotic encounters. Did you know that the Milky Way is the result of a long history of collisions and mergers with smaller galaxies? Just as rivers are formed by the joining of streams and tributaries, our galaxy grew by absorbing many of its neighbors, reshaping its structure each time this occurred. During the first billions of years after the birth of the universe, the cosmos was a much more compact and dynamic place. The first galaxies that formed were mostly small and fragile, known as dwarf galaxies. These, attracted by the gravity of the more massive ones, began to approach and eventually collide. When a dwarf galaxy got too close to the proto-Milky Way, it was literally torn apart and devoured, its stars and matter incorporated into the growing body of our galaxy. This process not only increased the mass of the Milky Way, but also enriched its chemical composition and diversified its star population. But what happens during a galactic merger? Is it an explosive collision or a slow gravitational embrace? Unlike the crash between 2 cars, stars within galaxies almost never collide directly due to the enormous distances between them. Rather, galaxies intertwine, and their gravitational fields generate intense tides that distort their shapes, mix their materials, and trigger episodes of star formation. In some cases, the remnants of these mergers are still visible today. Streams of stars, groups of globular clusters, and remnants of ancient satellite galaxies orbiting in the galactic halo. This process of galactic cannibalism was fundamental to the growth and evolution of the Milky Way. Each merger left traces in the distribution of stars and in the internal dynamics of the galaxy. For example, some of the oldest globular clusters orbiting the Milky Way actually formed in dwarf galaxies that were absorbed billions of years ago. Even today, the Milky Way continues to interact with nearby small galaxies, showing that galactic construction is a process that is far from over. In short, the Milky Way, far from being an isolated entity, is the result of a complex dance of encounters and mergers over cosmic time. The scars of these events are etched in the structure and composition of the galaxy, reminding us that the universe is a stage of constant change, where cooperation and destruction go hand in hand in the creation of something as grand as our galaxy. What role do black holes play in the history of the Milky Way? To answer this question, we first need to understand what these mysterious objects really are. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its pull. But why are they so relevant to the origin of a galaxy like ours? The answer lies in their gravitational influence and the role they play as invisible engines at the heart of galaxies. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A. This colossus has a mass equivalent to approximately 4 million suns. How did such a colossal object come to be? Theories suggest that during the early stages of the galaxy, small seeds of black holes, born from the collapse of very massive stars, began to devour material around them, merging with each other and growing through the accumulation of gas and stars. This process resembles a snowball rolling downhill. The more material it absorbs, the faster it grows. But what effects does this supermassive black hole have on the Milky Way? Although it sounds terrifying, most of the time this giant remains in a relatively calm state. However, during active phases in the past, it must have emitted enormous jets of energy and matter, influencing the rate of new star formation and the distribution of gas around it. These episodes can be compared to the eruptions of a cosmic volcano, capable of altering the galactic environment and slowing down the growth of the galaxy itself by expelling some of the gas needed to create new stars. Additionally, smaller black holes, known as stellar mass black holes, have also played a role in galactic evolution. They form after the explosive death of massive stars and act as cosmic recycling points. They often pull in material from nearby stars, redistributing heavy elements and energy into the interstellar medium. This interaction helps mix the essential ingredients for life as we know it. In summary, black holes are not only insatiable devourers, but also architects and regulators of the galaxy. Without them, the Milky Way would not have the same balance or dynamics. They constitute, in essence, the dark heart that beats at the center of our galaxy and the silent engine that has shaped its history since its earliest beginnings. What lies at the heart of the Milky Way? The galactic center is one of the most mysterious and extreme places in the entire known universe. There, in a region just a few light years in diameter, forces so powerful concentrate that they challenge our understanding. But what makes it so special? First of all, its density. While in the outer regions of the galaxy stars are separated by vast distances, in the galactic nucleus, stars are packed together as if they were spectators in a crowded stadium. This enormous concentration of matter creates a chaotic environment where gravity dominates and stellar movements are incredibly fast. At the very center lies Sagittarius A, a supermassive black hole with a mass equivalent to more than 4 million suns. How do we know it's there if black holes do not emit light? The key lies in the behavior of nearby stars, which orbit at astonishing speeds around an invisible point. It's like watching leaves swirling around a drain. Although we cannot see the water disappearing, the agitation reveals what is happening at the center. Astronomers have tracked these stars for decades, and thanks to their orbits, have been able to calculate the mass and exact position of this gravitational monster. But the galactic center is not just a black hole. It is a region rich in extreme phenomena. Giant clouds of gas and dust, bursts of X-rays and radio waves, and clusters of young and old stars coexisting in a hostile environment. Why are there so many young stars in such a dangerous place? The answer seems to lie in the abundance of gas, which fuels star formation even under the constant threat of the black hole. Thus, while some stars are born and others are devoured or expelled, the galactic center is a natural laboratory where the limits of physics are tested. Moreover, the nucleus of the galaxy plays a fundamental role in the evolution of the Milky Way. Gravitational interactions in this region can trigger bursts of star formation and expel jets of matter into interstellar space. It is believed that at certain moments in the past, Sagittarius A may have been much more active, illuminating the galactic center like a cosmic beacon. Could something like that happen again in the future? Although no one knows for sure, the center of the Milky Way remains one of the great enigmas of modern astronomy, a reminder that, even in our own galaxy, there is still much to discover. What do a galaxy like the Milky Way and a whirlpool in water have in common? At first glance, they seem like completely different worlds, but both share a shape that has fascinated astronomers and curious minds for centuries: spiral arms. But how do these stunning structures, which seem to draw a dance of stars around the galactic center, come into being? The answer is much more complex than it might seem, and takes us to the very heart of galactic dynamics. Contrary to what we might imagine, spiral arms are not like solid ribbons of stars traveling together, but rather areas of higher density, as if they were cosmic traffic jams. When gas and stars orbit the galactic center, they pass through these regions, and in doing so, the matter gets compressed. This phenomenon, known as density wave, is the main engine that forms and maintains the spiral arms. Thus, it is more accurate to think of the arms as waves in the sea through which boats pass, rather than as fixed tails chasing stars. And why are spiral arms so important for the life of the galaxy? The answer lies in the birth of new stars. These dense regions act as stellar incubators. As they pass through them, clouds of gas and dust get compressed and collapse, giving rise to generations of young bright stars. That's why spiral arms are often adorned with blue clusters and star-forming regions, as if they were fireworks in a vast cosmic celebration. Now, you might wonder if spiral arms are eternal. The reality is that their shape and number can change over time. Gravitational interactions with nearby galaxies, the presence of central bars, and even dark matter influence the evolution and stability of these arms. Some galaxies exhibit a well-defined pair of arms, while others show more chaotic patterns, as if they were scattered brushstrokes on the canvas of the universe. The Milky Way, for example, has several main arms and some minor ones, the result of billions of years of cosmic movements and encounters. In short, the evolution of spiral arms is a living testament to how the universe is in constant change. They are witnesses to the passage of time and key players in the history of star formation. Understanding how they arise and transform brings us closer to deciphering the mysteries of our galaxy and, ultimately, our own cosmic origin. What is, really, the galactic bulge? If we think of the Milky Way as a cosmic city, the bulge would be its historic center, the heart from where everything seems to have originated. It is a dense and compact region located in the core of our galaxy, made up of hundreds of billions of stars. But why is this center so different from the rest of the galaxy? Here, the stars are much closer together, as if they were tightly packed inhabitants in a central square during a grand celebration. The stellar density is such that, if we could live in the bulge, the night sky would be so filled with stars that there would barely be space for darkness. One of the big questions that astronomers have asked is, what is the galactic bulge made of and how did it form? Most of the stars that compose it are very old, some with ages exceeding 10 billion years. These stars are mostly metal poor, meaning they formed when the universe was still young and heavy elements were just beginning to appear. However, there is also a small fraction of younger, metal-rich stars, suggesting that the bulge is not a static fossil, but a region that has experienced several episodes of star formation. Did you know that the galactic bulge is not perfectly spherical? For a long time, astronomers imagined the center of the Milky Way as a simple sphere of stars. But more recent observations have revealed that it has a peanut, or elongated bar shape, a structure that challenges ancient ideas about galactic symmetry. This peculiar shape is the result of complex gravitational interactions and the internal dynamics of the galaxy. It's as if the bulge has been shaped and stretched by invisible forces throughout its history until it acquired the silhouette we know today. And what role does the bulge play in the evolution of the Milky Way? Besides being home to some of the oldest stars, the galactic bulge is the stage for extreme phenomena. The very center houses a supermassive black hole, Sagittarius A, whose gravitational influence affects the entire bulge and beyond. Additionally, the chemical composition of the bulge has served as a historical archive, allowing astronomers to reconstruct the early chapters of galactic life. Each star in the bulge is like a page from an ancient book, where the traces of supernova explosions, galactic mergers, and the recycling of matter can be read. Thus, the galactic bulge is not only a remnant of the past, but also a key piece for understanding the present and future of our galaxy. What lies beyond the bright disk of the Milky Way? Beyond the spiral arms and the central bulge extends a mysterious and diffuse region called the stellar halo. Why is the halo so important if it appears to be just an empty environment at first glance? The answer is fascinating. The stellar halo holds the keys to the origins and the oldest evolution of our galaxy. Although it contains only a small fraction of the total mass of the Milky Way, its role is fundamental in galactic history. The stellar halo is a kind of invisible sphere that envelops the galaxy. Unlike the disk, where stars orbit in orderly paths, the stars in the halo follow chaotic trajectories, like disoriented bees around a hive. Many of these stars are true cosmic fossils. They formed over 10 billion years ago and contain very low proportions of heavy elements, indicating that they were born when the universe was young, before successive generations of stars enriched space with new elements. How did these ancient stars end up there? Some were born in the primitive Milky Way itself, while others come from small galaxies that were devoured and torn apart by galactic gravity. Within the halo, we also find globular clusters, groupings of hundreds of thousands of stars that orbit far from the bulge and the disk. These clusters are like time capsules. By studying their composition and age, astronomers can reconstruct the early chapters of the Milky Way. Furthermore, the halo is not made up solely of stars, but also contains a large amount of invisible dark matter, which acts as an invisible scaffold and holds the galaxy together through its gravity. Without the dark matter of the halo, the Milky Way as we know it could not exist. One of the great surprises of the stellar halo is the presence of stellar streams, long trails that stretch like threads in the darkness. These streams are the remnants of ancient dwarf galaxies that were absorbed by the Milky Way. By tracing these streams, astronomers can read the history of encounters and mergers that our galaxy has experienced. Thus, the stellar halo is much more than just an empty frame. It is the living archive of the Milky Way, a silent testament to its origins, its conquests, and the mysteries that still remain for us to discover. Have you ever wondered why there are such ancient and dense star clusters floating in the galaxy's halo as if they were jewels suspended in the vastness? Globular clusters are collections of hundreds of thousands and even up to several million stars, all gravitationally bound in a compact sphere. These clusters orbit around the galactic center, but unlike the stars in the disk, their trajectories tend to be elliptical and chaotic, taking them to regions far from the galactic plane. What makes them so special? The answer lies in their age and composition. Globular clusters are true cosmic fossils, most formed over 10 billion years ago, shortly after the birth of the galaxy. Their stars, primarily old and low in metallicity, tell us what the universe was like in its early days when there were hardly any elements heavier than hydrogen and helium. In a sense, studying a globular cluster is like opening a time capsule that reveals the chemical and dynamic secrets of galactic formation. But what is the role of these clusters in the history of the Milky Way? Their very existence helps us reconstruct the galaxy's past. For example, the distribution and movement of globular clusters allow astronomers to identify traces of ancient mergers with other galaxies. Some clusters have arrived at the Milky Way as immigrants, bringing with them the imprint of their original galaxies, revealing that the Milky Way grew by consuming smaller ones. Moreover, these clusters have served as natural laboratories to test theories about stellar evolution, gravitational dynamics, and the presence of dark matter. A curious fact, although they may seem chaotic systems, globular clusters are surprisingly stable. Their stars are so densely packed that in the center of some clusters, the distance between stars can be as low as that between the Sun and the nearest star, Alpha Centauri. However, despite their proximity, actual collisions between stars are extremely rare. How is this possible? The answer lies in the vastness of space and the precision with which gravity maintains order within apparent chaos. Ultimately, globular clusters are key pieces in understanding how our galaxy formed and evolved, and they remain one of the main enigmas and treasures of the universe. Have you ever wondered why the atoms that make up your body, the water you drink, or even the air you breathe exist as we know them? The answer leads us directly to the fascinating process of galactic chemical evolution. Since its origins, the Milky Way has been a gigantic laboratory where elements have been forged, transformed, and mixed over billions of years. But how did this process happen? And why is it so crucial for the existence of life as we know it? It all began with a young galaxy, where hydrogen and helium dominated almost entirely. These primordial elements formed after the Big Bang were the basic material from which the first stars were born. In their cores, at unimaginable temperatures and pressures, these stars fused hydrogen into helium and, after exhausting their fuel, manufactured heavier elements like carbon, oxygen, and iron. When they exploded as supernovae, they released these materials into space, enriching the interstellar gas and sowing the seeds for future stellar generations. But how does this affect the composition of the Milky Way? With each cycle of stellar birth and death, the chemical content of the galaxy has been diversifying. The stars of older generations, known as population 2 stars, contain few heavy elements, while younger ones, like the Sun, have a higher proportion of these elements, referred to as metals in astronomical terms. It's as if the galaxy were a chef who, with each recipe, adds new ingredients to its mix, allowing for the formation of rocky planets, complex atmospheres, and eventually, life. Chemical evolution not only determines what stars and planets are made of, but it also reveals the history and rhythm of star formation in the galaxy. By analyzing the chemical composition of different regions and stellar populations, astronomers can reconstruct the mergers, collisions, and episodes of star formation that have shaped the Milky Way. Thus, every atom of iron in our blood or oxygen in our lungs tells an ancestral story, that of a galaxy in constant transformation where chemistry and physics intertwine to create the diversity of worlds we observe today. Ultimately, galactic chemical evolution is the key to understanding how a primordial gas cloud became a living, diverse galaxy. Thanks to this process, the Milky Way ceased to be a simple swirl of hydrogen and helium to become the home of stars, planets, and, at least in one corner of its vastness, beings capable of questioning their own origin. How is it possible that, billions of years after the birth of the Milky Way, there are still stars forming within it? The answer lies in one of the most fascinating and dynamic processes in the cosmos: continuous star formation. While we often imagine galaxies as static structures, they are actually true cosmic nurseries where the life and death cycle of stars never stops. But what ingredients allow this constant process? Mainly, enormous clouds of interstellar gas and dust, known as nebulae, which act as the raw material of the universe. Throughout the disk of the Milky Way, especially in its spiral arms, these clouds accumulate and, under certain conditions, begin to collapse due to gravity. It's as if a snowstorm transforms, grain by grain, into a compact ball. The gas and dust are compressed, the temperature rises, and eventually, a new star ignites. This process is so common that at any moment, in some corner of our galaxy, hundreds of stars are being born. Not all will have the same fate. Some will be massive and shine brightly for a few million years, while others, like our Sun, will live much longer. Where does this phenomenon occur most intensely? Mainly in the so-called stellar nurseries, regions like the Orion Nebula, where the density of gas and dust is so high that entire clusters of young stars form. These clusters are often so energetic that they illuminate their surroundings and sculpt the gas around them, creating landscapes of incredible cosmic beauty. But the birth of new stars is not an isolated process. Supernova, when they explode, disperse heavy elements and trigger shock waves that can ignite new waves of star formation in nearby regions. Thus, the death of one star can give rise to many others in a perpetual cycle of renewal. Will this process ever come to an end in the Milky Way? Eventually, yes. As the galaxy uses up its gas and dust fuel, the rate of star formation will decrease. However, this depletion is such a slow process that there are still billions of years of activity ahead. Every star born today is destined to become, in the future, part of the complex chemical and structural history of the galaxy. Continuous star formation not only keeps the Milky Way alive, but also sows the necessary conditions for the emergence of planetary systems and perhaps life in other corners of the cosmos. Interstellar gas is one of the most fascinating and essential ingredients in the evolution of the Milky Way. But why is something that, at first glance, seems so empty and dispersed so important? It turns out that, although interstellar gas occupies enormous spaces between the stars, it is the raw material from which new generations of celestial bodies are born. It is primarily composed of hydrogen and helium, but contains traces of heavier elements that have formed thanks to the life and death of previous stars. This mixture is, in a sense, the cosmic broth where the future of the galaxy is brewed. Have you ever wondered how an apparently inert gas cloud can become a shining star? The secret lies in gravity. When regions of interstellar gas cool down sufficiently, gravity can overcome the pressure that keeps the particles apart, causing these clouds to collapse. Thus, the gas begins to compress, and at the center, the temperature rises to millions of degrees. Then, a new star ignites. This process is not only fundamental for star formation, but it also recycles the heavy elements that previous generations of stars released upon dying, enriching the gas of the galaxy and allowing for the formation of planets and, eventually, life. But interstellar gas is not just a passive actor. It is also shaped and transformed by violent phenomena. Did you know that supernova explosions can create shock waves that compress the surrounding gas, triggering new waves of star formation? Additionally, stellar winds and radiation from the most massive stars can heat, disperse, and reorganize the gas, creating bubbles and filaments that span the entire galaxy. In a way, interstellar gas is like an invisible web that connects the fate of all stars, as what happens in one region can have consequences at enormous distances. Finally, the movement of interstellar gas is key to the overall dynamics of the Milky Way. As the galaxy spins, the gas moves in large currents and can form structures like spiral arms. This constant flow ensures that matter is distributed and that star formation regions remain active. Without interstellar gas, the galaxy would be a static and futureless place. But thanks to its presence, the Milky Way continues to be a living system, constantly changing and capable of giving rise to new stars, planets, and perhaps new forms of life. Did you know that the Milky Way is not alone in the vast universe? Around it orbit dozens of small galaxies known as satellite galaxies, swirling like bees around a cosmic hive. These dwarf galaxies, although much less massive, play a fundamental role in the history and evolution of our galaxy. But which ones are the most famous? And why have they captured the attention of astronomers for so long? Two of the best known are the Large Magellanic Cloud and the Small Magellanic Cloud. These galaxies, visible to the naked eye from the southern hemisphere, are like noisy neighbors orbiting the Milky Way at a distance of hundreds of thousands of light years. It is speculated that, in the past, both have interacted dramatically with our galaxy, losing some of their gas and stars in the process. In fact, the so-called bridges and streams of gas between the Milky Way and the Magellanic Clouds are evidence of these cosmic encounters. It is fascinating to think that, on galactic timescales, these interactions can trigger waves of star formation in both the satellite galaxies and the Milky Way itself. But why are there so many dwarf galaxies around us? One of the most accepted theories suggests that, in the primitive universe, large galaxies like ours grew from the merging and absorption of many small galaxies. Some survived this process and became trapped in the orbit of the Milky Way, witnesses to a more turbulent era. By observing these satellite galaxies, astronomers can reconstruct the history of the Milky Way, almost as if they were reading the oldest chapters of a cosmic book. Moreover, The ongoing interaction with these dwarf galaxies has not only left scars in the form of stellar streams and remnants of dark matter, but has also chemically enriched our galaxy. Each time a satellite galaxy gets too close, part of its content may be absorbed by the Milky Way, bringing new elements and stars into the mix. Surprisingly, new satellite galaxies are still being discovered today, some so faint that they barely stand out among the stars of the halo. All of this confirms that the Milky Way and its satellites form a dynamic and ever-evolving system where each small galaxy has a story to tell in the grand narrative of the cosmos. Did you know that at the edges of the Milky Way, there are traces of ancient galaxies devoured by our own galaxy? These traces are known as stellar streams. Imagine a river of stars silently winding through space, remnants of dwarf galaxies that once had their own identity, but today exist only as scattered threads of light and matter. But how is it possible to detect these subtle vestiges in the vastness of the cosmos? The answer lies in the precise movement of the stars and their chemical composition, which act as cosmic fingerprints revealing their extragalactic origin. Stellar streams are true living fossils. They form when the gravity of the Milky Way captures and tears apart smaller galaxies that pass too close. This process, known as galactic cannibalism, has not only altered the structure of our galaxy, but has also enriched its halo with new stars and globular clusters. A famous case is the Sagittarius stream, formed by the remnants of the Sagittarius dwarf galaxy, which is currently being absorbed and extends in a giant arc around the Milky Way. What do these stellar flows tell us about the past of our galaxy? They reveal that the Milky Way is the result of countless encounters and mergers over billions of years. Moreover, the study of stellar streams allows us to reconstruct the hidden history of the Milky Way, as if we were reading an ancient cosmic scroll. By analyzing the distribution of these stars and their trajectories, astronomers can deduce how many galaxies have been devoured and how these events have shaped the current structure of the galaxy. It is fascinating to think that many of the stars that now form part of the galactic halo, or even some that we see in the night sky, came from distant places and witnessed titanic collisions. Could there be more stellar streams waiting to be discovered? Undoubtedly. Current technology, such as the Gaia mission from the European Space Agency, is allowing us to identify new streams of stars with unprecedented precision. This opens the door to better understanding the process of galactic growth and uncovering the deepest secrets of the Milky Way. Ultimately, stellar streams are much more than mere remnants. They are living proof that our galaxy continues to evolve and adapt, building its identity from the fragments of others. What makes the galactic disk of the Milky Way so special? If you stop to think about the structure of our galaxy, the galactic disk is like the main track of a great cosmic carousel. There, most of the stars, including our own Sun, orbit around the galactic center in nearly circular paths. But how did this gigantic and thin structure form? And what secrets does it hold about the origin of the Milky Way? The galactic disk began to take shape when enormous clouds of gas and dust, slowly rotating in the primitive halo of the galaxy, collapsed under the force of gravity. As they contracted, the material gained an increasingly spinning motion, similar to a pizza tossed in the air that flattens and stretches while it spins. This dynamic led to the gas and dust being distributed in a thin sheet, where conditions were ideal for star formation. Thus, over billions of years, the disk became populated with generations of stars, many of them organized into striking spiral arms. Did you know that the galactic disk is neither uniform nor static? It is actually composed of two main components, the thin disk and the thick disk. The thin disk is where most young stars, molecular clouds, and regions of active star formation are found. This disk is only a few hundred light years thick, but its diameter extends over 100,000 light years. In contrast, the thick disk contains older and less metallic stars, revealing clues about the primitive times of the Milky Way. The difference between the two disks is like comparing the layers of a cake. One is thin and recent, the other is thicker and older, each with its own story. The galactic disk not only houses stars and gas, but also open clusters, interstellar dust, and an intricate network of magnetic fields. Despite the apparent calm when observing the night sky, the reality is that the disk is in constant motion and transformation. Stars are born, evolve, and die. Gas is recycled, and the spiral arms unfold like waves on a lake. Even impacts from dwarf galaxies and gravitational disturbances can cause ripples and structures in the disk, as if a stone had been thrown into a calm surface. Could the galactic disk exist without these dynamic processes? The answer is no. It is precisely the continuous interaction between gas, stars, and gravitational forces that maintains the vitality of the disk. This dynamic environment is essential for the formation of new stars and planets, and for the chemical evolution of the galaxy. Thus, the galactic disk is not only the stage where much of the Milky Way's history unfolds, but it is also the cradle of the cosmic diversity we observe today. What would happen if suddenly a star the size of the Sun reached the end of its life and exploded with unimaginable energy? Supernovae are precisely that. Stellar explosions so powerful that for a few weeks they can shine brighter than an entire galaxy. But beyond the spectacle, why are they so important for the existence and evolution of the Milky Way? To understand their relevance, let's think of the galaxy as a gigantic chemical laboratory. The first stars were born from hydrogen and helium, the simplest elements in the universe. However, life and planets require more complex elements: carbon, oxygen, iron. Where do these essential ingredients come from? The answer lies in supernovae. When a massive star explodes, it forges and disperses these heavy elements into interstellar space. It's as if a cosmic piñata released treasures into the universe, allowing new generations of stars and planets to emerge with greater chemical richness. But supernovae don't just sow the basic materials for life. Did you know they also shape and regulate the development of the galaxy? The shockwaves from these explosions travel through the interstellar medium, compressing gas clouds and triggering the formation of new stars. It's an endless cycle. Stars are born, live, explode, and help others to arise. Without supernovae, the Milky Way would be much more static and poor in chemical variety. Thanks to them, the galaxy is in constant renewal and transformation. Another surprising function of supernovae is their influence on galactic dynamics. By releasing enormous amounts of energy, they can generate galactic winds capable of expelling gas outside the galaxy's disk, thus regulating the amount of matter available for future stellar generations. These processes also affect the distribution of dark matter, altering the structure and evolution of the galaxy itself. So, although they may seem like mere cosmic catastrophes at first glance, supernovae are actually the great agents of change and diversity in the Milky Way, responsible for the astonishing variety of stars, planets, and life that exists today. Where exactly are we in the vastness of the Milky Way? The Sun and the solar system, despite being the epicenter of our daily lives, are merely a tiny dot in the vast galactic structure. If the Milky Way were a gigantic city with hundreds of thousands of streets, the solar system would reside in one of the peripheral neighborhoods, far from the bustling center. We find ourselves in the so-called Orion Arm, a minor subdivision between two main spiral arms, about 27,000 light-years from the galactic center. This location is not a coincidence. It is far enough from the core to avoid intense radiation and chaotic conditions, but also close enough to be bathed in the richness of elements forged in previous generations of stars. Is the Sun a common star within the Milky Way? Although it may seem special to us, the Sun is a G-type spectral star, known as a yellow dwarf. Of the hundreds of billions of stars in the galaxy, many are smaller and cooler, like red dwarfs, while others are blue and white giants, much more massive and fleeting. What truly distinguishes the Sun is that it hosts a diverse planetary system, with at least 8 planets, countless asteroids, and comets. However, recent studies suggest that planetary systems are quite common in the galaxy, although the variety and configuration of worlds can differ greatly. How does the solar system move within the Milky Way? We often imagine the Sun as stationary in space, but in reality, it travels at a dizzying speed of about 220 kilometers per second, completing an orbit around the galactic center every 225 million years. This journey has been termed the cosmic year. During its course, the solar system passes through clouds of gas, spiral arms, and regions where star formation is active. It is even believed that in the past, these travels have influenced episodes of climate change and extinctions on Earth by exposing us to different cosmic environments. Is there any relationship between our galactic position and the emergence of life on Earth? Surprisingly, yes. Our current location, far from areas where supernovae frequently explode or where stellar density is too high, has provided a kind of cosmic refuge. This has allowed life to evolve relatively undisturbed for billions of years. If the solar system were closer to the galactic center, radiation and intense gravitational activity could have hindered or even prevented the evolution of complex life forms. Thus, our corner of the Milky Way is not just a simple data point of location, but a crucial factor in the history of life on our planet. At the heart of the Milky Way, there exists a surprising and fundamental structure, the central bar. What do we mean when we talk about a bar in a galaxy? Imagine the galactic center, not as a simple spherical core, but as a kind of luminous, elongated bar made up of hundreds of billions of stars, gas, and dust. This bar runs through the central bulge and connects the spiral arms, functioning almost like the axle of a cosmic wheel. But how do we know this bar exists if we are immersed in one of the arms and cannot observe the galaxy from the outside? Astronomers have used sophisticated maps of stellar distribution and observations in infrared wavelengths capable of penetrating the dense cloud of interstellar dust to reveal the existence of this central structure. What is the purpose of the central bar in a galaxy like ours? Far from being a mere cosmic ornament, the central bar plays an essential role in galactic dynamics. It acts like a gigantic conveyor belt, channeling gas from the outer regions to the galactic center. This flow of material fuels the formation of new stars and, at times, provides fuel to the supermassive black hole at the core. In fact, it is believed that the presence of a bar can trigger intense bursts of star formation in the central bulge, altering the evolution of the entire galaxy. In terms of analogy, the bar would be like a spoon stirring the ingredients in a large cosmic bowl, mixing gas and stars to shape and energize the galactic center. But how does a central bar form? The answer lies in the gravitational forces of the galaxy itself. When the galactic disk becomes massive enough and dynamically unstable, the orbits of the stars begin to preferentially align, creating the elongated structure we know as a bar. Surprisingly, not all spiral galaxies possess a bar. It is estimated that about 2 out of 3 do have one. This phenomenon can arise at different times in a galaxy's life and, in some cases, can even disappear or reappear, depending on cosmic interactions and internal evolution. The central bar is not a static structure. It slowly rotates, dragging along stars and gas. This movement has fascinating consequences. It can provoke density waves that propagate along the disk, influencing the formation of the spiral arms. Additionally, the central bar may provide clues about the history of past collisions and mergers of the Milky Way, as these events can strengthen or weaken the bar over time. Thus, the central bar is not only the dynamic heart of our galaxy, but also a key to understanding its past and future evolution. What other mysteries could this structure, so close yet so difficult to study from our own perspective, be hiding? Have you ever wondered how a galaxy like the Milky Way remains alive and dynamic for billions of years? The secret lies, in part, in the gas flows that traverse the galactic disk and halo like true cosmic arteries. This gas, composed mainly of hydrogen and helium, travels through the galaxy, fueling the formation of new stars and recycling materials that have been processed by previous generations of stars. Without these flows, the galaxy would be like a stagnant river. It would lose the ability to renew and change. But where does this gas come from, and where does it go? A significant portion comes from the intergalactic medium, that is, the space that exists between galaxies. Occasionally, enormous clouds of gas fall towards the Milky Way, drawn by gravity, and are incorporated into its disk. This process is known as gas accretion and is fundamental to maintaining the rate of star formation. At the same time, there are gas flows that go in the opposite direction. They are expelled by supernova explosions and stellar winds, creating a kind of galactic cycle where gas rises and falls, enters and exits, as if the galaxy were breathing. And why is this constant movement of gas so important? Because it determines the galactic chemistry and consequently the possibility of life. When fresh gas enters the galaxy, it is often poor in heavy elements. However, as stars are born, live, and die, they enrich the gas with new elements like carbon, oxygen, and iron. These materials, essential for planet formation and eventually for life, are dispersed and mixed thanks to the gas flows, ensuring that each new generation of stars has access to increasingly complex raw materials. A fascinating fact is that these flows are not uniform or predictable. Sometimes, enormous jets of gas, known as galactic fountains, can extend thousands of light-years beyond the visible disk. Additionally, interactions with nearby dwarf galaxies can trigger real gas storms, altering the structure and pace of the Milky Way. Thus, gas flows not only act as the circulatory system of the galaxy, but also connect it with the cosmos on a grand scale, reminding us that the Milky Way is a living being in constant transformation. What role do magnetic fields play in a galaxy like the Milky Way? While we often think of gravitational forces, gas, and stars when talking about galaxies, magnetic fields are invisible yet fundamental players in galactic dynamics. Imagine the Milky Way as a vast cosmic city. The magnetic fields would be like electrical energy networks running through the streets and buildings, influencing traffic movement and the functioning of the entire city. But how do they actually affect the galaxy? Galactic magnetic fields extend throughout the disk, halo, and spiral arms, and although they are millions of times weaker than the Earth's magnetic field, their influence on a galactic scale is immense. One of their most important functions is to guide and shape the flow of interstellar gas. This gas, primarily composed of hydrogen, is the essential material for the formation of new stars. The magnetic field can channel these gas flows, either hindering or favoring the concentration of matter in certain regions. Thus, magnetic fields act as invisible highways, directing the traffic of gas and dust, modulating star creation in different areas of the galaxy. Another fascinating question is, where do these magnetic fields come from and how are they sustained? Astronomers believe that the initial fields, although extremely weak, emerged shortly after the birth of the galaxy. Over time, plasma movement and galactic rotation amplified these fields through a process known as the galactic dynamo. It's similar to how our planet's magnetic field is generated, only on a much larger scale. This mechanism ensures that magnetic fields are renewed and maintained over billions of years, creating complex and sometimes surprising patterns, such as spirals that follow the shape of the galactic arms. You might wonder, what evidence do we have of these magnetic fields if we can't see them? Scientists have developed clever ways to detect them, using the polarization of light and radio waves emitted by electrons spiraling around the lines of the magnetic field, a phenomenon called synchrotron radiation. Thanks to these observations, we know that magnetic fields are not only present, but also affect the movement of charged particles, protect regions from cosmic radiation, and even help shape the giant bubbles created by supernova explosions. In short, the magnetic fields of the Milky Way are fundamental to understanding the evolution and behavior of the galaxy. Although invisible to the naked eye, Their imprint is present in star formation, gas dynamics, and protection against radiation, acting as conductive threads that connect the different galactic components. The study of these fields is still full of mysteries, but each advance brings us a little closer to deciphering the complex and fascinating workings of our home in the universe. What happens when two galaxies meet in the vastness of space? Although it seems that the universe is infinite and empty, galaxies are in constant motion, and over billions of years, their paths may cross. The Milky Way is no exception. It has had close interactions with several neighboring galaxies, and indeed these encounters have been fundamental to its evolution. One of the most anticipated collisions is the one that will take place with the Andromeda Galaxy. Can you imagine the outcome of two cosmic giants slowly approaching each other over millions of years? The gravity of both galaxies is pulling them together, and astronomers have calculated that in about 4 billion years, the Milky Way and Andromeda will collide. But contrary to what we might think, it will not be a violent crash like two cars on a highway. In reality, the distances between stars are so vast that most will simply pass by without colliding, although the gas and dust will interact, generating new waves of star formation and completely transforming the structure of both galaxies. But Andromeda is not the only guest at this cosmic dance. Another galaxy, the Sagittarius dwarf galaxy, is already being absorbed by the Milky Way. This process, which has been happening for billions of years, has left behind streams of stars that traverse the galactic halo, like traces of a history of galactic cannibalism. Why does this happen? The Milky Way, being more massive, exerts a gravitational pull that ultimately dismembers its smaller neighbors. Each time it engulfs a dwarf galaxy, the Milky Way gains mass, new stars, and greater complexity in its internal structure. And what consequences do these encounters have on life within a galaxy? Galactic mergers can trigger episodes of intense star formation, modify the shape of the galaxy, and redistribute interstellar gas and dust. Additionally, they can alter the orbits of solar systems, although the probability of our own solar system being directly affected by a collision is very low. However, these encounters are responsible for much of the diversity we observe in the galaxies of the universe. In a sense, the Milky Way is the result of countless encounters, mergers, and absorptions, making it a true survivor and witness to the dynamics of the cosmos. Thus, encounters with neighboring galaxies are not mere astronomical anecdotes, but essential processes for understanding how galaxies form, grow, and evolve. Through these interactions, the Milky Way has changed time and again, adapting and transforming, leaving visible traces in its structure and in the distribution of its stars. Each encounter is like a chapter in a cosmic story, a story that is still far from over. What does it take for a planet to be born on the vast stage of the Milky Way? The answer begins in the clouds of interstellar gas and dust that float between the stars. These clouds, known as nebulae, contain the fundamental ingredients: hydrogen, helium, and a small but crucial proportion of heavier elements such as carbon, oxygen, iron, and silicon. But how does this dispersed material transform into solid bodies? The key lies in gravity. When a region of the cloud becomes dense enough, gravity initiates a collapse process, forming a star at the center and, around it, a rotating disk of gas and dust, the protoplanetary disk. At what point does the true magic of planetary formation begin? Within that disk, dust particles start to collide and stick together, forming increasingly larger clumps. It's as if millions of dust motes in a room began to group together and, little by little, built a mountain. These small bodies, called planetesimals, can reach sizes of several kilometers and, thanks to their own gravitational forces, attract more material, growing relentlessly. Over time, some of these planetesimals become protoplanets, and from here, future planets emerge. Why aren't all planets the same? The distance from the central star is crucial. Close to the star, heat prevents light compounds, such as water or methane, from condensing. That's why rocky and small planets, like Earth or Mars, form in these inner regions. Further out, where temperatures are lower, ices and gases can accumulate, giving rise to giant planets like Jupiter and Saturn, with dense and extensive atmospheres. It is in these distant environments where planetary diversity multiplies, giving rise to icy worlds, gas giants, and even rogue planets that have been ejected from their original systems. Did you know that planet formation is not a rare phenomenon in the Milky Way? Astronomers have discovered thousands of exoplanets orbiting other stars, and observations suggest that most stars have some type of planetary system. This implies that the processes that led to the creation of our own solar system are common throughout the galaxy. Moreover, the heavy elements necessary to form solid planets were not always present in the universe. It was the evolution of previous generations of stars, which released these materials upon dying, that allowed the Milky Way to become a true nursery of planets. Thus, each planet is the result of a long chain of cosmic events, a story of stellar recycling that ultimately made it possible for worlds like ours to exist. How long has the Milky Way been in existence? This seemingly simple question is actually a fascinating puzzle for modern astronomy. To answer it, scientists have had to resort to ingenious tools and clues hidden in the oldest corners of the galaxy. The age of the Milky Way is not measured by counting rings like in trees, but by analyzing the oldest stars, globular clusters, and the chemical elements that make up our cosmic home. One of the most commonly used methods involves studying globular clusters, those swarms of hundreds of thousands of stars that orbit in the galactic halo. Some of these stars are so old that they formed shortly after the birth of the universe, over 13 billion years ago. Astronomers calculate the age of these stars by measuring their brightness, temperature, and composition. A kind of stellar archaeology that reveals that the Milky Way began to form when the universe was still young, just about 500 million years after the Big Bang. But how can we know if these stars truly belong to the original Milky Way, or if they were captured from other galaxies? This is where studies on stellar chemistry come into play. By analyzing the ratio of light and heavy elements in the oldest stars, scientists can trace the galactic genealogy. Stars with very few heavy elements, known as population 2 stars, are considered living fossils that formed in the early stages of the galaxy. Thus, we can deduce that the initial structure of the Milky Way began to consolidate between 13 and 14 billion years ago. However, the galaxy we inhabit today is the result of a dynamic and prolonged process. The Milky Way did not come into existence in a single moment. Rather, it grew through mergers with smaller galaxies and by accumulating gas and stars over billions of years. It's like building a city. First, the main streets are laid out, and then, little by little, neighborhoods and buildings are added. Therefore, the age of the Milky Way can refer both to its oldest components and to the structure we currently recognize. Knowing the age of our galaxy is not just a matter of curiosity. It helps us understand the rhythms of the cosmos, the history of matter, and ultimately, our own origin. Each ancient star and each globular cluster is a page in the book of the Milky Way, written billions of years ago and still legible to those who know where to look. The next time you gaze at the night sky, remember that you are observing a relic of the past, a silent witness to the oldest history of our universe. How is it possible to investigate such a vast and complex structure as the Milky Way when we can't even step outside of it to see it from the outside? This is one of the questions that most intrigues astronomers and, at the same time, one of the greatest challenges of modern astrophysics. To decipher the secrets of our galaxy, scientists have developed various techniques that combine observation, cutting-edge technology, and a lot of creativity. Observing the Milky Way is like trying to reconstruct the image of an immense city while standing right in its center, unable to fly above the buildings. A key method has been the use of telescopes that capture different types of light, beyond what our eyes can see. For example, radio telescopes allow us to detect signals emitted by hydrogen atoms, the most abundant element in the galaxy. This reveals detailed maps of gas clouds, and helps us understand how the spiral arms are distributed. On the other hand, telescopes that operate in the infrared can penetrate the interstellar dust that normally blocks our view, allowing us to see hidden regions like the central bulge or the galactic core. But it's not just a matter of looking. To know the distance to the stars, scientists use the parallax method, which involves measuring the slight change in position of a star as the Earth moves around the Sun. Thus, little by little, the three-dimensional puzzle of our galaxy comes together. But how do we know how fast the Milky Way is moving, or how its various stellar populations are distributed? The answer lies in the study of light spectra. By analyzing how the light from stars breaks down into colors, astronomers can determine their chemical composition, age, and relative speed with respect to Earth. The Doppler effect technique, for example, allows us to know if a star is moving closer to or farther away from us. Additionally, modern astrometry, driven by missions like Gaia, has made it possible to accurately measure the position and movement of billions of stars, facilitating the creation of extremely detailed maps of the Milky Way. Another fundamental approach is the observation of globular clusters and stellar streams. These groupings and flows of stars act as fossil witnesses of galactic history. By studying their distribution, age, and movement, scientists can infer past events, such as collisions and mergers with other galaxies. Even the search for dark matter, this invisible but dominant component in the galaxy, is based on observing how stars and gas move under the influence of a mass that emits no light, but whose gravity is impossible to ignore. In summary, investigating the Milky Way is a monumental challenge that requires a combination of innovative methods and increasingly precise tools. Each technique, from observation across multiple wavelengths to the analysis of stellar motion, contributes an essential piece to the grand mosaic of our galaxy. Thus, even though we are trapped within this immense stellar system, science allows us to peek, little by little, at the true shape and nature of our cosmic home. How is it possible that we know what our galaxy looks like if we are inside it? This is one of the most fascinating questions in astronomy. Unlike observing a city from a drone, studying the Milky Way from Earth is like trying to draw the blueprint of a house while trapped in one of its rooms. However, astronomers have developed ingenious strategies to map our galaxy, revealing secrets that remained hidden for centuries. For a long time, the Milky Way was a mystery, wrapped in interstellar dust and vast distances. But how did scientists manage to see through that veil? The key lies in observing different types of light. While our eyes can only perceive a small range of the spectrum, radio telescopes and satellites capture wavelengths like infrared and radio waves. In this way, they have been able to identify the spiral arms, the central bulge, and the halo surrounding the galaxy. The famous hydrogen gas, for example, emits a signal at 21 centimeters, allowing the structure and extent of the Milky Way to be traced even in the regions most obscured by dust. One of the most impressive advancements in galactic mapping has been the Gaia mission by the European Space Agency. Why is it so relevant? Because Gaia has measured with unprecedented accuracy the positions and movements of over 1 billion stars. This has allowed the creation of three-dimensional maps that show not only the shape of the galaxy, but also how its stars move, discovering stellar streams and remnants of ancient galactic mergers. Thanks to this data, we now know that the Milky Way is not a static structure, but a dynamic system in constant transformation. Another intriguing question is, how much do we still not know about our own cosmic home? Despite significant advancements, the map of the Milky Way remains incomplete. There are areas, such as the so-called zone of avoidance, hidden behind dense clouds of dust where visible light cannot penetrate. However, each new technique and observation brings astronomers closer to solving the galactic puzzle. Thus, the maps of the Milky Way have become true cosmic atlases, where each star is a key piece of a story that we have only just begun to decipher. What would you think if I told you that there is an echo of the birth of the universe? a kind of fossil imprint that we can still detect in all directions. That echo is the cosmic microwave background radiation, and its existence is one of the most compelling pieces of evidence for the origin and evolution of the cosmos. But what exactly is this radiation, and why is it so important for understanding how the Milky Way was formed? About 13,800 billion years ago, the universe was an incredibly hot and dense place, where matter and energy were so intertwined that light could not travel freely. However, when the cosmos expanded and cooled, enough protons and electrons combined to form hydrogen atoms. At that moment, light became free and began to travel through the universe, becoming the cosmic microwave background radiation that we can observe today. This radiation is like a photograph of the universe when it was only a few 100,000 years old, long before galaxies, stars, or planets existed. Now, how does this ancient glow help us understand the origin of the Milky Way? The small temperature and density changes that we observe in the cosmic microwave background radiation are the seeds of all the structures that exist in the universe. Imagine the surface of a calm lake, and suddenly, small ripples begin to form. Those ripples represent the tiny variations in the density of the early universe. Over time, gravity amplified those differences, allowing gas to clump together and, millions of years later, form the first galaxies, including ours. Studying the cosmic microwave background radiation not only reveals the age and composition of the universe, but also allows us to reconstruct the process by which the large cosmic structures formed. Thanks to missions like COBE, WMAP, and Planck, scientists have been able to map these tiny fluctuations with astonishing precision. Did you know that these variations are so small that the temperature difference between the coldest and hottest points is just a few millionths of a degree? And yet, those tiny differences were enough to trigger the formation of entire galaxies. Ultimately, the cosmic microwave background radiation is the key to answering one of the deepest questions in astronomy. How did complexity arise from simplicity? Deciphering this ancient echo allows us to trace the history of the Milky Way back to its most remote beginnings, when the universe was just starting to structure itself. Thus, every time astronomers analyze this radiation, they are, in a way, observing the first chapter of the history of our galaxy. Did you know that our galaxy, the Milky Way, is not alone in the vast universe? In fact, it belongs to a kind of cosmic neighborhood called the local group. But what exactly is the local group, and what is the importance of our galaxy within this context? Imagine the local group as a small galactic town, where each galaxy is a house inhabited by billions of stars. Within this town, the Milky Way is one of the two main mansions, alongside the Andromeda galaxy. Both lead a group of over 50 galaxies, most of them small and dwarf, that orbit or interact gravitationally with these giants. The Milky Way and Andromeda are the dominant galaxies due to their size and mass, exerting a kind of gravitational influence over their neighbors. Have you ever wondered how this affects their evolution? The answer is fascinating. The gravity of these two giants has shaped the arrangement and fate of the smaller galaxies in the local group, attracting them, merging with them, or even stealing some of their stars and gas. For example, the Milky Way is surrounded by a court of satellite galaxies, such as the large and small Magellanic Clouds, which are slowly being torn apart by the force of our galaxy. When we compare the local group to other galactic groups, we notice that it is relatively modest. There are much larger and denser clusters, such as the Virgo cluster, home to thousands of galaxies. However, the local group is the perfect environment to study how galaxies interact and evolve in a less chaotic and more intimate context. The distance between the Milky Way and Andromeda is about 2.5 million light-years, which may seem immense, but on the scale of the universe, it's as if two islands were separated by a narrow sea. One of the big questions that arise is, what will be the fate of these neighboring galaxies? Astronomers have discovered that the Milky Way and Andromeda are on a slow but inevitable collision course. In about 4 billion years, both will merge into a new giant galaxy, completely altering the landscape of the local group. This process of encounters, mergers, and transformations is essential to understanding the life cycle of galaxies and their role in the large-scale structure of the universe. Thus, the Milky Way is not just a lonely island of stars, but part of a dynamic community where each member, big or small, contributes to the collective story of the cosmos. Studying the local group helps us understand not only our place in the universe, but also the fundamental processes that have shaped the galaxy we inhabit. What will happen to the Milky Way in billions of years? Although it may seem that our galaxy is eternal, it is actually in constant transformation, and its future is marked by cosmic events of enormous magnitude. One of the most striking events that astronomers have predicted is the collision between the Milky Way and the Andromeda Galaxy. But what will this galactic encounter be like, and what consequences will it have for stars, planets, and possibly life? The Milky Way and Andromeda are like two giants dancing in space, slowly moving closer to each other due to the gravity they exert on one another. It is estimated that in about 4 billion years, both galaxies will begin to merge in a process that will last hundreds of millions of years. Despite the magnitude of this collision, individual stars within each galaxy are unlikely to collide directly, as the space between them is immense compared to their size. It is more probable that they will experience a complex exchange of positions, as if millions of fireflies crossed paths on a night without touching. Does this mean the end of the Milky Way as we know it? In a sense, yes. The merger will give rise to a new galaxy, likely elliptical in shape, which some scientists are already calling Lactomede. The Sun and our solar system will be dragged into new orbits, perhaps farther from the galactic core, or even expelled to the outskirts of the new structure. However, by then, life on Earth may have disappeared, either due to the evolution of the Sun itself or other cosmic processes. In addition to the collision with Andromeda, the Milky Way will continue to interact with its satellite galaxies, such as the Large and Small Magellanic Clouds, which are being gradually absorbed. These minor mergers continue to feed the growth and evolution of the galaxy, bringing in new stars, clusters, and interstellar matter. It's as if the Milky Way is constantly reshaping itself, adding pieces and losing others in an endless cycle of change. Could we someday see the night sky radically transformed? During the merger with Andromeda, the sky would be filled with new stellar formations, dust arcs, and regions of intense star formation, creating spectacles that we can only imagine today. However, these processes occur on timescales that challenge our human understanding. The future of the Milky Way is a story of encounters, changes, and mergers, where the only constant is transformation itself. The galaxy we inhabit today is just a chapter in a cosmic epic that will continue long after we have vanished. In recent years, the Milky Way has ceased to be merely the backdrop of our solar system and has become the star of some of the most fascinating discoveries in modern astronomy. Did you know that it has recently been possible to map the position and movement of over 1 billion stars with an unprecedented level of detail? This has been made possible thanks to missions like Gaia, which have revealed not only the spiral structure of our galaxy, but also the existence of stellar streams, true remnants of dwarf galaxies that have been absorbed throughout the history of the Milky Way. It's as if the galaxy has scars that tell the story of its turbulent past of mergers and cosmic encounters. But how old are these merger events? One of the most surprising findings is the identification of an ancient collision, known as Gaia Enceladus, which occurred about 10 billion years ago. Astronomers have managed to distinguish stellar populations that originated in that dwarf galaxy, and that today are part of the galactic halo. Discovering these remnants is akin to analyzing the rings of a tree to understand the seasons it has experienced. Each of these mergers has left a chemical and dynamic imprint that allows us to reconstruct the biography of the Milky Way. Another intriguing question is, what lies at the galactic center? In recent years, the existence of a supermassive black hole at the core of the Milky Way, called Sagittarius AI, has been confirmed. Thanks to telescopes like the Event Horizon Telescope, scientists have been able to observe its shadow, obtaining the first indirect images of this gravitational monster. Additionally, stars known as S-stars have been discovered, which orbit at dizzying speeds very close to the black hole, allowing us to test theories of general relativity under extreme conditions. Equally fascinating is the finding that the Milky Way is not a static structure. Recent observations have detected that the galactic disk is undulating, as if it were a kind of moving sea. These waves could be a consequence of encounters with dwarf galaxies, or even with dark matter. This is complemented by the detection of new streams of cold gas flowing toward the galactic center, fueling star formation. Each of these discoveries not only answers questions, but also opens new mysteries, reminding us that our galaxy still holds secrets waiting to be revealed. What would you think if I told you that every time you look at the night sky and see that whitish band crossing the firmament, you are actually looking at the plane of a gigantic cosmic city that contains hundreds of billions of stars? The Milky Way is much more than just the backdrop of our nights. It is a natural laboratory full of secrets. For example, did you know that the Sun, along with its planets, is about 27,000 light-years from the galactic center and takes approximately 225 million years to make a complete orbit around the galaxy? That means that since the first dinosaur appeared, Earth has barely completed a single galactic turn. Another fascinating curiosity is that, although the Milky Way seems stable and calm, it is actually in constant motion and transformation. Our galaxy is literally devouring smaller galaxies around it. Evidence of this can be seen in the so-called stellar streams, true rivers of stars that are the remnants of these cosmic encounters. Furthermore, the Milky Way is not as clean as we might imagine. It is surrounded by an invisible halo of dark matter, which represents most of its mass, and without which it simply would not exist in its current form. Have you ever wondered how big the Milky Way is compared to other galaxies? Although it is impressive, it is not the largest in the neighborhood. The Andromeda galaxy, for example, surpasses it in size and number of stars. However, the Milky Way is special. New stars are forming within it at a rate of about 1 per year, and its galactic disk is so thin in proportion to its diameter that if we reduced it to the size of a vinyl record, it would be thinner than a sheet of paper. And as if that weren't enough, the Milky Way is full of mysteries yet to be solved. It is estimated that there could be more than 100 billion planets in our galaxy, many of which could have conditions favorable to life. In fact, some astronomers believe that there are rogue stars ejected from the galaxy, traveling alone through intergalactic space at unimaginable speeds. Thus, the Milky Way, far from being just the stage of our existence, is a universe in itself, full of stories, enigmas, and wonders waiting to be discovered. What makes life exist on Earth and not on most of the planets we know? The answer lies not only on our planet, but in the very heart of the galaxy we inhabit. The Milky Way has been the stage for a series of cosmic processes that, astonishingly, have allowed life to flourish as we know it. But why this galaxy and not another? Is there something special about the Milky Way that offers us unique conditions for the existence of living beings? To begin with, the position of the solar system within the Milky Way is crucial. We are located in a region known as the inner edge of the Orion Arm, a relatively quiet strip, far from the bustling galactic center where black holes, intense radiation, and supernova explosions are much more frequent. This location could be compared to living on the outskirts of a city, close enough to access resources, but far from the constant danger posed by the chaos of the center. Thanks to this position, Earth has enjoyed long periods of stability, essential for life to evolve and thrive. Another fascinating aspect is the chemical richness of the Milky Way. Successive generations of stars that have been born and died in our galaxy have seeded space with heavy elements like carbon, oxygen, nitrogen, and iron. These ingredients are fundamental for the formation of rocky planets and for the construction of complex organic molecules, the building blocks of life. Without this cosmic factory of elements, Earth would be just a barren rock, incapable of harboring oceans, atmosphere, or any form of life. And what about the broader galactic environment? The Milky Way is not alone. It interacts with other dwarf galaxies and receives flows of fresh gas that fuel the formation of new stars and, potentially, new planetary systems. This constant recycling acts as a renewal engine that keeps the galaxy active and capable of creating favorable conditions for life time and time again. It's like a balanced ecosystem where each element plays a role in keeping the life cycle going. Finally, the long-term stability of the Milky Way has been a key factor. Unlike galaxies subjected to constant collisions or with extremely violent activity, our galaxy has maintained for billions of years a relatively conducive environment for the development of life. This combination of abundant chemistry, strategic location, and cosmic stability has made it possible for, in a corner of the universe, questions like this to arise. Are we the only conscious beings in the entire galaxy, or does the Milky Way hide other secrets yet to be discovered? Is it possible that the Milky Way still holds fundamental secrets about its own origin? Despite all the scientific advancements, there are questions that continue to baffle astronomers. For example, while we know that our galaxy emerged from the merger of gas clouds and small galaxies, the exact process that led to the formation of its current structure remains an enigma. Why does the Milky Way have the specific number and shape of its spiral arms? Although computer models can simulate certain patterns, the deep reason behind their design and stability is not entirely clear. Another of the great mysteries is the nature of the dark matter that makes up most of the mass of our galaxy. We know it's there because its gravity holds the structure of the Milky Way together and affects the movement of the stars. But what is it really? So far, scientists have not been able to detect it directly or identify its components. It's as if we were trying to reconstruct the history of a house just by observing the shadows of the walls, without being able to touch the bricks. Will we ever discover the true nature of this invisible matter? Delving even deeper, the question arises about the supermassive black hole at the galactic center. How did it form so quickly in the early days of the universe? Although there are theories suggesting it was born from the collapse of enormous gas clouds or the merger of smaller black holes, the speed and exact mechanism of its growth remain subjects of debate. Was this black hole the main engine in the organization of the galaxy, or just another product of the initial cosmic chaos? Finally, there is the mystery of life itself. Although the Milky Way contains hundreds of billions of stars and likely billions of planets, we have yet to find clear signs of life beyond Earth. Is our galaxy a privileged place for the emergence of life, or are we simply an exception in an immense collection of uninhabited worlds? Each astronomical discovery, each new observation, brings us a little closer to understanding the secrets of our galaxy, but the universe always seems to have one more card up its sleeve. How much longer will these great mysteries remain hidden? Have you ever wondered how a luminous band in the night sky has inspired myths, art, and science throughout history? The Milky Way is not only our galactic home, but it has also been an inexhaustible source of imagination for humanity. Since ancient times, civilizations around the world have looked up at that diffuse strip in the darkness and sought to make sense of it. Why does it appear as a river of light crossing the heavens? For many, the answer was magical and deeply symbolic. In ancient Greece, the Milky Way had a divine origin. According to mythology, it was created when the milk of the goddess Hera spilled across the sky. In fact, its name comes from the Greek, meaning path of milk. But the Greeks were not the only ones weaving tales around this mysterious band. The Maya saw it as the great celestial serpent, while in Chinese tradition, it was the heavenly river that separated two eternal lovers, the Weaver Princess and the cowherd, allowing them to reunite only once a year. Isn't it fascinating how, without contact between them, so many cultures imagined rivers, paths, or sacred routes traversing the sky? Beyond mythology, the Milky Way has also played a fundamental role in the practical lives of people. Ancient civilizations used it as a reference for navigation and agriculture, guiding themselves by its position to mark seasons and routes. Australian Aboriginals, for example, considered it the home of ancestral beings and used it as a natural calendar. In Africa, some cultures interpreted it as the trail of dust raised by the gods as they walked across the sky. Can you imagine relying on the Milky Way to organize daily life? With the advent of modern science, the fascination with the Milky Way has not diminished. Rather, it has evolved. Galileo, by directing his telescope toward that whitish band, discovered that it was made up of countless stars, forever transforming our view of the universe. However, the cultural influence of the Milky Way remains alive. Today, we find it in literature, film, music, and even in our everyday language. How many times do we use the expression "to be among the stars" to talk about impossible dreams or limitless creativity? In short, the Milky Way has been much more than a simple astronomical object. It has been a bridge between science and myth, inspiration for art and philosophy, and a silent witness to the evolution of humanity. Looking at the Milky Way is, in a way, looking at our own stories and questions projected onto the cosmos. What new tales and discoveries will it inspire in the future? What makes a galaxy like the Milky Way so fascinating and, at the same time, so crucial for our existence? If we think of the universe as an immense ocean, the Milky Way is the island where life as we know it emerged. But how is it possible that among billions of galaxies, just in this one, did the precise conditions arise for us to evolve, to question our own galactic origins? The answer lies in an incredible chain of events. From the collapse of primordial gas clouds, through supernova explosions that seeded essential elements, to the gravitational dance of stars, clusters, and planets. Each piece fit into a cosmic puzzle that, even today, we are still trying to decipher. The Milky Way is not simply a collection of stars spinning in space. It is a living testament to the evolution of the universe, an archive of stories written in the light of its oldest stars and in the chemical composition of its gas clouds. Did you know that we still retain traces of galaxies devoured by ours, like scars in its stellar halo? These streams of stars, invisible to the naked eye, reveal cosmic battles that took place millions of years before the Sun even existed. What mysteries still lie hidden in the depths of its core, where a supermassive black hole marks the rhythm of the galactic heart? Studying the origin of the Milky Way is, in a way, like opening the pages of a book that tells the story of everything around us. Each scientific discovery, each new image captured by telescopes, adds a word, a phrase, to that infinite narrative. Why do the spiral arms take on that elegant and almost hypnotic shape? How have invisible forces, like dark matter and magnetic fields, guided the fate of billions of stars? These are questions that show us how much we have learned, but also how vast what remains to explore is. Ultimately, understanding the origin of the Milky Way not only satisfies our curiosity, but also connects us to something much larger. It reminds us that we are part of a cosmic process that began billions of years ago and continues to unfold as we speak. How far will our questions reach? Will we be able to find all the answers? Or will the galaxy continue to hold secrets that challenge our imagination? What is certain is that when we look towards the bright center of the Milky Way on a clear night, we are contemplating the past, present, and future of our home in the universe.